Let's do one more example of finding a particular solution using undetermined coefficients. You can tell from the title of this slide that something is probably going to go a little wonky, so we're going to have to be especially thorough when we do this. So let's find a particular solution for this one, y double prime minus 3y prime plus 2y equals e to the 2x. So let's make a guess for our particular solution. So what sorts of things, when we start taking derivatives, would we end up with an exponential? Well, as we've seen before, we should probably guess that same exponential. And then let's take a couple derivatives so we can plug our guess for a particular solution into the original differential equation. So first derivative is 2 times a e to the 2x. Second derivative is 4 times a e to the 2x. And then plug these into the original differential equation. 4a e to the 2x minus 3 times the first derivative, 2a e to the 2x, plus 2 times the 0th derivative, so the original guess, a e to the 2x. And this is supposed to be equal to e to the 2x. All right, so let's simplify the right-hand side. It looks like we've got 4 minus 6 plus 2. Wait, 4 minus 6 plus 2. This left-hand side is 0. But we were supposed to have some equation that let us find an undetermined coefficient. So something went wrong here. Something went very wrong. Since we didn't get an equation that let us determine the undetermined coefficients, that means our guess here for what a particular solution should look like was wrong. This is sort of math's way of telling us that we made a bad guess. Right? We asked, hey, are there any solutions that look like this? And the math said, no, there are no solutions that look like that. So what happened and how could we fix it? Well, you might have noticed that we never actually found the complementary solution for this example. Usually we do that first, so let's go ahead and find the complementary solution. To do that, we need to write down the associated homogeneous equation, so y double prime minus 3y prime plus 2y equals 0. This has characteristic equation m squared minus 3m plus 2 equals 0. This one factors. This is m minus 2 times m minus 3. Sorry, m minus 2 times m minus 1. So m can be 2 or 1. And so our complementary solution is c1 times e to the 2x plus c2 e to the 1 times x. Okay. And actually, now this shows us why our guess was a bad guess. This guess that we made, some constant times e to the 2x, it's actually part of the complementary solution. So remember, what that means is this complementary solution, if you plug this into the left-hand side, you get 0. That's what the complementary solution is, because it's a solution to the associated homogeneous equation. So we accidentally made a guess that makes this left-hand side of the equation 0. So that's a bad guess because we didn't want the left-hand side to be 0. We wanted it to be equal to e to the 2x. So this was a bad guess because the guess that we wanted to make overlaps with the complementary solution. So that's the unfortunate situation that we're in. The guess we wanted to make overlaps with the complementary solution. So how can we fix this? Well, we need to figure out some other type of function that we could use for a guess whose derivatives involve e to the 2x. And you might recall from our work with homogeneous linear equations that there is another kind of function whose derivatives spit out some factors of e to the 2x, or some terms involving e to the 2x. And that is x times e to the 2x. So let's try, instead of e to the 2x, x e to the 2x. Of course, when we start taking derivatives, this is going to make things messier because now we have to do a product rule, but you know, that's life. So derivative here is, so I'm just moving this constant outside the derivative. So now we have to do the product rule. So e to the 2x plus 2x e to the 2x. And let's factor out the e to the 2x. So that's a e to the 2x times 2x plus 1. Okay, and now second derivative. So again, let's factor out that, or move that a outside the derivative. And then we're going to do a product rule. So a derivative of the exponential part spits out a 2 from the chain rule. 2 times e to the 2x times 2x plus 1 plus e to the 2x with no derivative, and then the polynomial part here with a derivative, so that's 2. And we can simplify all of this. So this is a times e to the 2x. And then let's see, we have 4x right there. And then for constants, we have a 2 and another 2, so plus 4. Okay, so now we have our guess and its first two derivatives. We can plug this into the original differential equation, which was, let's see, y double prime minus 3y prime plus 2y equals e to the 2x, right? Yes. Okay, plugging everything in, we get a e to the 2x times 4x plus 4 plus, no, minus 3 times y sub p prime, and that's right here, a e to the 2x times 2x plus 1 plus 2 times y sub p, which is ax e to the 2x. And this is supposed to be equal to e to the 2x. All right, so now we can simplify this. Let's see. We're going to, every term has an e to the 2x, so let's factor that all out. And every term also has a factor of a, so let's factor out the a's. Everything that's left just has different powers of x, so let's gather up like terms of x. So for our x terms, there's one here, there's one here, there's one here. So for our x terms, this first one is 4. And then the second one, we get a minus 6. And then the third one, we get a plus 2. Notice that these add up to 0, which actually is what we want because this left-hand side is supposed to be equal to the right-hand side, but the right-hand side doesn't have a factor of x. So it's good that these add up to 0. That's a good sign. Plus, and now let's get all the constant parts. So there's a 4. Here's a plus 1, but don't forget the times minus 3. So minus 3, and then plus 2. Okay, and this is all supposed to be equal to e to the 2x. So we get a e to the 2x times 1 plus 2, 3 equals e to the 2x. And now we can use this equation to solve for our undetermined coefficient a. So divide both sides by e to the 2x, and we're left with a is a third. So now we have a particular solution, 1/3 times x e to the 2x. Okay, the general idea here is, sort of looking back on what just happened, when we had this overlap with what we wanted to guess for our particular solution and the complementary solution. So we took our original guess and we just multiplied it by x. Now it's not obvious that that's the right thing to do, but it turns out that it works in this case, and in fact it works in any case where undetermined coefficients works. If you ever have an overlap with your original guess and your complementary solution, just take your original guess and multiply it by x, and then check again. If there's still overlap, then multiply it by x again. This is why it's actually important to find the complementary solution first, because you need to know if there's this overlap between the complementary solution and the particular solution that you're guessing. So just to summarize all of the undetermined coefficients cases we've looked at so far, what you guess for your particular solution depends on what the right-hand side, the inhomogeneous term in your equation is. If it's an exponential, then just guess that exponential. If it's sines or cosines that have the same angular speed in there, then just guess combinations of sines and cosines. It is important to include both sines and cosines because both of these derivatives of sines and cosines both give you sines and cosines. If your inhomogeneous term is a polynomial, then guess a polynomial of the same degree. And we didn't look at an example of this case, but if you have a product of any of these possibilities, like say e to the x times e to the 2x, so this is a polynomial times an exponential, then you just take the product of the guesses that you would make. So if this were your g of x, your inhomogeneous term, then your guess for a particular solution would be a degree 1 polynomial, so ax plus b, times an exponential, so e to the 2x. So the guess for our first one times the guess for our second one. All right, and then we saw there was one exception. If your guess for your particular solution overlaps with the complementary solution, just multiply your guess by a power of x until they don't overlap anymore.